All right, so let's look at an idea behind or application of reactions in aqueous solution, which are titrations. And our titrations basic idea is that, let's say you have to determine the concentration of a solution, but you know some information about another solution. And you can use the reaction between the two components of those solutions to gauge some information. So a typical example is an acid-base reaction. So like you have hydrochloric acid, when you want to determine the concentration of that solution. So if you have a uh, basic solution, so like sodium hydroxide, and you have the concentration and the volume of that, then you're able to determine some information about your hydrochloric acid solution. So exactly meaning that if you set up an experiment in some manner where you can connect the number of mole of hydrochloric acid with the number of mole of sodium hydroxide, then you know the information that you need, right? So that's where we have titrations. Okay, so what do we need to get of our sodium hydroxide? So that's what this above bullet points tell you. It says you can do a titration if the following are met. So I'm just going to discuss that now. So what do we need about the sodium hydroxide? Well, if we have the concentration, so that's usually something that we know about our sodium hydroxide solution. If we have that, and let's say we're going to add the sodium hydroxide to our unknown analyte solution, so meaning our hydrochloric acid solution, and we measure how much we need to add, how much of this solution we add. And there was some point that we know, okay, right, the reaction, we've added enough sodium hydroxide. Then in principle, right, we could determine how much sodium hydroxide we've added, so the number of mole of sodium hydroxide we've added. And hence we can use the reaction equation, so meaning that over there at the top over here, we can relate that back to our, over there, to our number of mole of hydrochloric acid, because it reacts in a 1-to-1 relationship. So using the volume added of the sodium hydroxide, the known concentration, we can relate the number of mole of sodium hydroxide added to the number of mole of our hydrochloric acid in our reaction beaker. All right. And if we also know the volume of our sodium hydroxide, of our hydrochloric acid, we can combine that information and we can then determine the concentration of our original hydrochloric acid. We can then go further and we can determine things like the mass of the hydrochloric acid or the molar mass or a whole bunch of other things. Sorry, I made a mess there. We can, so I said, like the molar mass of hydrochloric acid or like just the mass or whatever. All right, so we can then determine a whole bunch of things. So how do we set up an experiment like this where we can measure these things? Well, that is what we call a titration. Now, a titration requires a burette, and this is a burette, this glass instrument over here, and it contains the base or the concentration of the solution that we know. So of the solution with the known concentration. All right, so that is what we add. And in the flask here at the bottom, so this has the sodium hydroxide in it. All right, and it allows us, you will see it's graduated, so meaning you can measure. So here you can measure what the volume is that you add. All right, so it allows you to know how much of the substance you've added. At the bottom, you put the analyte, so meaning the hydrochloric acid that you're interested in. But now we still need to have something that indicates to us when the reaction is complete. So meaning when have we added enough base? When have we added enough sodium hydroxide? And what we use to do that is exactly that, an indicator. And an indicator is a dye, so meaning something that changes color depending on the pH. So the example here uses phenolphthalein, and phenolphthalein has is colorless in the pH less than 7, and it's pink when the pH is larger than 14. So your question might be, okay, all right, so how does that help us at all? But if you think about it, when the reaction starts, so at the start here, how much sodium hydroxide is at the bottom here? Your amount of sodium hydroxide at the bottom here should be 0, right? And the amount of hydrochloric acid should be, well, that's what we're determining, but it should not be 0, right? There should be more, there's still some hydrochloric acid left. And as you start adding sodium hydroxide and sodium hydroxide to the hydrochloric acid, at some point in the future, what should happen to these two things? At some point, they will be equal, right? So at some point, there will be a point where these two numbers are going to be equal. So meaning where the number of moles are going to be equal. And what happens at that point? What happens to the pH? Well, at that point, your pH should be completely neutral, right? Because there is no acid, there's no base. There's exactly um, you know equal amounts of both of these things, because you've added the sodium hydroxide so slowly. There's no more acid or no more base. They've exactly equal amounts. And if you were to add, let's say, one more drop, I'm going to draw a little droplet here. One more drop of the sodium hydroxide. What happens to the pH? This is not larger than 14, sorry, it's larger than 7. The pH is larger than 7. What happens to the pH? Well, it just goes above 7, right? Because you've now added a drop more base to it. In other words, it means the sodium hydroxide becomes in excess. And phenolphthalein is pink in basic conditions. It's colorless in acidic conditions, and it's pink in basic conditions. But now our HCl, so the amount of moles of HCl is 0, because it's all being consumed up. And the number of mole of the sodium hydroxide is larger than 0. So there's a bit more, because there's one drop extra. So that's the principle of a titration. We take it all the way from where the HCl is in excess and there's no sodium hydroxide. We start adding them. At some point, they're equal. And then eventually, there's just a drop more. And that tells us something. This reaction, we're actually looking for this point where these two things are equal. Because what can we do then? Then we can do this. We can say, well, once we know where they are equal, we're able to relate those two quantities. Because if we know the point where they are equal, in other words, where that indicator is just about to going to change color, because you'll see that it's going to be a very light pink color. That indicator changes color, and then we can relate the amount of sodium hydroxide added to the amount of hydrochloric acid. And then we can do all those other fancy things. Now that point has a very special name. It's called the equivalence point. All right, and it's the point where these two quantities are equal, or differently put, it's where the amount of hydroxide is added is equal to the amount of hydronium present in the flask. Okay, you can read about it in this paragraph. It says the same thing, but I have a short video for you that perhaps shows the process of titration very nicely, which we can look at just now. All right, so just give me 2 seconds. Right, so there you see the burette, which of course contains your sodium hydroxide solution. And here at the bottom is your HCl plus your indicator. And we'll add the indicator just now. So there's the indicator, the phenolphthalein indicator. And notice how the indicator is completely colorless at the moment. But now as we start adding the base, you see there's a slight pink tinge to it. And as we start adding more and more base, the pink tinge struggles to go away. But as we stir, it it goes away eventually. But the pink, little slight pink color remains until we reach the equivalence point. And at the equivalence point, we're going to remain with a slightly pink colored solution, which you will see just now. And of course, then at the equivalence point, you know the amount of base added equals the amount of acid in the flask originally. But my question now is, what happens if we add more base? What do you expect to see with the flask here at the bottom? And I mean, hopefully you've predicted that your phenolphthalein is, or your flask is just going to become more darkly colored, right? So you'll see that just now, if you add more base, it just becomes more darkly colored. But the question is, does that help you in any case? No. That just means you're over titrated, and that does not help you at all. That doesn't give you any information. All right. Thank you for watching.